Okay, so the last topic we want to cover in this section is parametric polymorphism. Right, so we've already seen ad hoc polymorphism, and so this is where we could define a function with the same name to operate on multiple kinds of data, right? So recall our add function here that could work on different numbers of integers or on different types, right? Or we can go further back and consider overloading something like plus, right? So we've seen plus working on integers or floating point numbers. That's all ad hoc polymorphism. Parametric polymorphism is different in that there's some type parameter that we want to make use of and sort of fill that in. So if we have a list, we can have a list of integers or a list of strings. And so here we see a definition in C and Pascal for an integer list. And one can imagine writing an append function for such a list, right? That we're going to march down these pointers, these next pointers, creating new cells, filling in the data field for these cells, and create a new list out of, in this case, list 1 and list 2. So that's one way we could think about doing this, is sort of making this duplication. So, one thing that's interesting is that we never examine the contents of the data field, right? We may copy it from one list into another, but we never do anything except just copy those bits over, right? So in that sense, this function is somehow independent of the type of the list elements. It doesn't, for instance, try and add up all the values in the list, right? So if we have a sum function, adds up the values of a list, it's not at all independent. It's dependent upon that integer type because it's adding them together. So in this case, append is something that's independent of that type. So I may ask, can we define an append function that works on all types of lists? And so the idea here is to allow what we call type variables or parameters in type expressions. Right? So we'll make use of the Greek letter alpha here as our type parameter. Right? So we can say, okay, well, our append is going to be a function that takes a list of type alpha, another list of type alpha, and gives us a list of type alpha. So if we have lists of integers, we could take two lists of integers and get back a list of integers. And in that case, we would think of sort of instantiating alpha with the type integer. And we have to do this consistently so that every alpha in our type expression is instantiated with the same value. Right? So we can't have the last alpha be integer and this alpha, the second one, be string. Right? That's not allowed here. Right? Every instance of alpha has to be the same. And so thus we could think of this append function as working over all kinds of lists, not just lists of integers or strings or floats, but lists of anything. And so now we have a function that works over many kinds of data, but we only provide one implementation. Right? In ad hoc polymorphism, we provided an implementation for every instance of that function for the types it was meant to work over. Right. So here again, we sort of get this notion that alpha gets instantiated with the desired type. Right, so this is what we call parametric polymorphism. Right? The idea here is that types are parameterized by other types. And so this is why we've referred to list as a type constructor. It's something that if we plug in the required types, it will generate this list type for us. Right? So list itself is not a type. It's a constructor of types. It's a function that if we give it a type, will give back another type. If we give it the int type, it gives us back the list of integer type. Right? And so then functions over these types work uniformly for all instances at those types. All right, so in a C-like language, right, we can think of taking our structure like this and saying, all right, we wanted to get rid of our particular data and make this be a void pointer, for instance. Right? This gives us a way to do things in a sort of parametric polymorphic way. The problem is it's not type safe anymore. But if we're generating C code, right, so if we have a ML compiler that translates down to C, we could do all the static analysis and type safety checking during that compilation, and so C would be a reasonable target language for a type safe language. but it's a difficult language to write type-safe programs in when we have too much use of these void pointers and such. C++ templates are similar to parametric polymorphism. They're not quite the same thing, right? So in a C++ template, we don't have one implementation of, for example, append for all the different types. Instead, we treat that append function as a template, and we generate multiple copies of append for every instance type that it's used at. But this is not quite the same thing. Early C++ compilers had some trouble with this, that the type checking happened after the templates were instantiated, so you get type errors on the generated code. Modern C++ compilers do a better job with this. Right, but ML is really sort of well known as being the first language that provided parametric polymorphism and strong type checking in the same package. Right, and so the nice thing is we only had to check that, for instance, with append, L1 and L2 have the same type. We don't care what the component types are as long as they're the same. And that's where we just check that whatever we instantiated alpha with, they were the same value, the same instantiation. Right, and thus append works for all lists in a type-safe way. So this is something that, as I said, was developed in ML. It's sort of a cornerstone of functional programming, and it's something we'll take a deeper look at when we talk about functional programming in more depth. Right? And that's something we'll start on Monday when I return. So that's it for this section. We'll see you next week.